Good afternoon, all of you. So let us continue our discussion on sinusoidal steady state AC circuits. So yesterday we saw that in the steady state of a sinusoidal AC circuit, all voltages and currents have the general form, functional form, which can be written as A sine omega t plus phi. Okay, and then we said that we can express this function as a shortcut by a complex number which is A by root 2 angle phi. This shorthand notation is called the Phasor value or Phasor representation. Okay. Now the beauty of this Phasor representation is that if we have a resistance R and if the Phasor value of the current flowing through it is I, the Phasor value of the voltage across it is V bar, okay, then V bar by I bar, this ratio is equal to R, a constant. Similarly, if we have an inductor with inductance L, and again the current is I bar, voltage across it is V bar plus minus, and suppose omega is the angular frequency of the supply, okay, then we can write that V bar by I bar is equal to L omega J or J omega L. Okay. Similarly, if we have a capacitor with capacitance C, current, Phasor value of the current is I and the voltage Phasor value is V, again omega is the angular frequency, then the ratio V bar by I bar is 1 over J omega L. So in all these cases we see that the voltage and current, their Phasor values are proportional to each other. Okay, and this right hand sides, that is the ratio of voltage and current, they are called impedance, okay, which is analogous to resistance in a DC circuit. In DC circuits, the ratio of voltage and current is resistance. Here the ratio of Phasor voltage and Phasor current is called, in general, the impedance. Okay, so therefore the voltage and current, their Phasor values are related by an equation very similar to Ohm's law, even in AC circuits, steady state AC circuits. Okay.
Excuse me, sir.
Yes, please.
So in the third one, it should be 1 by J omega C.
Yeah, thanks a lot. Yeah, this should be J omega C. Thank you. Yeah. So this is the beauty of the Phasor values. Another fact, okay, suppose I have two currents, call it I1, which is Im1 sine omega t plus phi 1, and another current I2 Im2 sine omega t plus phi 2, and let the corresponding Phasor values be like this. So let me write the Phasor values here. So for the first one, it is Im1 by root 2 angle phi 1, which can also be written as, so this is a complex number, we can also write this as Im1 by root 2 e to the power j phi 1. Okay. Similarly, the phasor value of the second current will be Im2 by root 2 angle phi 2. Now suppose these two currents are entering a node in a circuit. Okay, suppose this is I1, this is I2, and we want to get the total value of the current entering the node. Okay, so that will be I1 plus I2. How much will that be? That is basically the sum of these two quantities. Copy, paste this plus this. Now, if you simplify this expression of I1 plus I2, you can write it as Im3 sine omega t plus phi 3 for some value of Im3 and phi 3. What will be that value, those values of Im3 and phi 3? So for that you have to simplify this using trigonometric rules. For that you may have to do say half a page of calculation, which may take around 5-6 minutes. Okay, so that I will keep as your homework. Okay, so simplify this using trigonometric formulas. Okay, but we can always show that the sum of two sinusoidal functions is always going to be a third sinusoidal function. Now let me ask, what will be the value, phasor value of the of this current I1 plus I2? Okay, so if I call this as I1 bar, this as I2 bar, then what will be I3 bar? That is sum of I1 plus I2. The answer is it will be equal to I1 bar plus I2 bar. Okay, without even doing this simplification using trigonometry, we can simply say that the phasor value of this I1 plus I2 will be phasor value of I1 plus phasor value of I2. Okay, without much calculation. Why is that so? Let me try to justify why this is the case. Okay, so suppose I give you the phasor value, say I1 bar, okay, and then I want to get the functional form of corresponding to I1 bar. What do I have to do? So this is actually equal to Im by root 2 e to the power j theta. So what I have to do, I have to first multiply this number with e to the with root 2 and e to the power j omega t, and after that we have to take the imaginary part of the product. Okay, so if you do that, I think you can see that you will get Im1 sine omega t plus this is phi 1 plus phi 1. Okay, so this is the basically rule for getting the functional form from the phasor value. Now if we do the same thing, copy paste, if I apply the same rule on this number, say I1 bar plus I2 bar, okay, if you do here also I have one more term, plus Im2 by root 2 e to the power j phi 2. Okay, you multiply this with root 2 e to the power j omega t and then take the imaginary part. Okay, if you do that, I hope you can see what we are going to get. We will get basically this quantity. Right? So that means the function corresponding to this phasor I1 plus I2 is this Im1 sin omega t plus phi 1 plus Im2 sin omega t plus phi 2. Okay? So what it shows that if you know the phasor values of two sinusoidal function, then the phasor value of the sum of these two sinusoidal will be just the sum of the two phasors. So that's way it's very helpful to do calculations. Now, one more thing. Okay, so consider this function 0 sin omega t plus phi. What will be the phasor value of this number? Anyone? It will be just 0. That means 0 plus j0, complex 0. Okay. Now, with all these observations that we have done, now we can write that, we can say that Kirchhoff's voltage law for AC circuits can be written as that the say Kirchhoff's current law first. Kirchhoff's current law in an AC circuit, sinusoidal steady state, can be written as that the sum of phasor values of currents, yes, entering a node should be equal to 0. In the same way, Kirchhoff's voltage law for AC circuits can be written as the sum of phasor values of voltages entering a in a loop should be equal to 0. 0 plus j 0. Okay. So now we see that with the help of phasor values, it is very easy to write Kirchhoff's current law, voltage law, as well as the relation between voltage and current for resistance, inductance and capacitance. Okay. So yesterday we were discussing why it is difficult to work with AC circuits compared to DC circuits. But now we see all these problems that we discussed yesterday are solved when we use phasor values. Okay, so we shall see some examples of this. Okay, so first, consider that we have R resistance, inductor and a capacitor all in series. Okay, and suppose I tell you that the current flowing through them, the phasor value of the current is I bar. Okay, and I ask how much is the voltage across it, phasor value of the voltage from here to here. Okay, how do we get that? Okay, so we may first break the voltage into small parts. Let this voltage be VR plus minus, then this voltage across the inductor be VL plus minus and VC plus minus, Okay, then we can write V bar total voltage will be equal to VR plus V, all these are phasors, plus VL plus VC. Now how much will be VR? That will be I multiplied by R. VL will be j omega L multiplied by I, and plus 1 by j omega C multiplied by I. So together all this I can write I common R plus j omega L plus 1 by j omega C. Okay, so this we will call as the total impedance of this path or branch, total impedance. Okay, let me call this Z. Okay, Z is again a complex number. Okay, and so we see that like in DC circuits, resistances in series get added when we compute the equivalent resistance. Similarly here, impedances, complex impedances get added when they are in series connection. Okay, now this is the total impedance, which is equal to R plus j omega L plus, I can write this also in this way, j common omega L minus 1 by omega C, because 1 by j is equal to minus j. Okay, now so in general impedance, complex impedance will always have two parts, real part plus an imaginary part, A plus JB, like this. Okay, so let me just give you some definition. This real part is called the resistance. This is the name, okay, of this real part. And the imaginary part is called the reactance. Okay, and yeah, now also observe that if we have only this inductor, only inductor L is there, this capacitance is not there, okay, then this imaginary part will be positive. Okay, so reactance of an inductor, call that inductive reactance, that will be positive, and the capacitive reactance in the same way will be negative. Okay, if we don't have this inductor L there, then we have minus j by omega C, so that part is negative. Okay, now we can represent these things pictorially. Okay, so suppose so we saw that.
Sir?
Yes.
Sir, can you explain this like positive and negative for inductive and capacitive reactance? What is meant by that?
Yeah, so the inductive reactance or inductive impedance is how much? So that is, if you have an inductor, then its reactance or impedance is j omega L. Okay, and I mean by positive I mean the if you ignore the j part, then this omega L part is positive. But if we consider a capacitance, then that is 1 by j omega C, which is equal to minus j by omega C. Okay, so let me write j outside. Then this I mean that this minus 1 by omega C, this part is negative. Okay.
Okay, sir, got it.
Now, yes, so Z in this case we saw is equal to R plus j omega L plus minus j by omega c. Okay. So all these are in general complex numbers. So sometimes we can pictorially represent them in a complex plane. Suppose this is the real axis, this is the imaginary axis. Then R is a purely real number. Okay, so we can draw a pure real number like this. This is R. Okay, and then j omega L. This is a purely imaginary number with the imaginary part being positive. Okay, so let me draw that here. Okay, so this will be representing j omega L, and minus j by omega c, that will be a number downwards, minus j by omega c. Now if you add all these complex numbers in a way we add vectors, okay, using parallelogram law, okay, so what we will get, so we may start this minus j omega c from here. Okay, so let this be minus j by omega c. Okay, then if you add this part with R, this will be the total vector, total impedance Z. Okay, so this is called the impedance diagram. This kind of diagrams are called impedance diagrams. Okay. Also, there is another pictorial representation which is very useful, that is called Phasor diagram, where we will show complex values of voltages and currents, in a circuit. Okay, so if you consider this particular circuit, let me copy it below for quick reference. Let me keep it here. Okay. Then again let me draw a complex plane, real axis, imaginary axis. Okay, and this I bar is a complex number. Suppose I bar is here. Suppose this is the I bar. Then VR, this is equal to I times R. Okay, so how can we draw this vector VR? This will have same phase angle as I bar, but magnitude will be different. Okay, so maybe it will be here, VR bar, which is equal to I times R. Then if you consider VL bar is equal to I times j omega L. So we are multiplying I with j, which will rotate this vector by 90 degree counterclockwise, right? So that will be possibly here somewhere. This is VL bar. Okay. The length should be proportional to the product of I bar and omega L. And similarly, if I draw VC bar, which is the voltage across the capacitance, I times minus j by omega c, where will that be in the phase, in this complex plane? That will be 90 degree rotated in clockwise direction. Yeah, right. So this will be VC bar. So this angle should be 90 degree. This angle should also be 90 degree. Okay, so this is called the Phasor diagram. Okay, and let me clean up a bit. Now, if we add these three voltages VL, VC and VR, okay, So suppose VC is here up to just a second. Suppose this is VC bar. Now let me add VC bar with VL bar. What can I do? I can draw this VC bar starting its tail from here and draw it parallelly like this. Okay, so then this point is VL bar plus VC bar. Now if you add this with VR, let me use the parallelogram rule, then this is the total voltage VL plus VC plus VR. Okay, and then so this is the total voltage V, and here we have the current I. Okay, fine. So any questions so far?
Sir?
Yes.
Sir, am I audible, sir?
Yes, yes.
Sir, my doubt was like when we did it in series, we were adding, right, sir, the impedance, I mean those resistance sort of things. Can we do that also in parallel? Can we apply this thing that we are doing in if we are keeping inductance parallel to capacitor and resistance?
So you cannot
can we do like 1 by R1? 1?
Yeah, you cannot add them directly, because when even in resistances, even you are considering resistances in parallel, what do you add? You add basically reciprocal of resistance.
Yeah, 1 by R1 plus
right.
1. Yeah, reciprocal.
Exactly
so
the same
that
thing.
Same thing we can do here.
Yes, yes, you are absolutely right. So if we have, let me tell it briefly, since you have asked. If you have R, then L, then C, okay, then if this voltage is V bar from here to here, plus minus, and then this impedance is R, this is J omega L, then this is 1 by J omega C. Okay, if I call this current as I1 bar, phasor values all are I2 bar, and this is I3 bar. Okay, then we will get I1 bar equal to V bar by R, then I2 bar will be V by J omega L, and I3 will be V by 1 by J omega C. Okay, then the total current I, okay, total current I will be I1 plus I2 plus I3. Okay, so that will be V common, and we have 1 by R plus 1 by J omega L plus 1 by 1 by J omega C. Okay, so then we can write from here that V bar by total current I bar will be equal to 1 over 1 by R plus 1 by J omega L plus 1 by, so let me write it just J omega C. Okay, so this, call it Z, complex number, is the total impedance, equivalent impedance.
Got it, sir. So we can do it similar to DC,
Exactly
if we use phasor.
Exactly, yeah, that is the main point. Okay, and also let me just tell you, so if we have any impedance, suppose Z is impedance of some circuit, then the quantity, call it y, which is 1 over z. This is called the admittance, okay, which is analogous to conductance in resistive circuits, I mean DC circuits. And if it has two parts, say y, say ay plus jby, then this real part is called conductance, and this imaginary part is called the susceptance. Okay, these are just definitions. So main point here,
Parallel LCR circuits there in our syllabus?
yes, why not? Yeah.
Okay.
And so the main point here is that when we use phasor values, we can deal with AC circuits in steady state, sinusoidal, exactly in the way like DC circuits. Okay, and the only difference is that in DC circuits, voltage, currents, and resistance, they are real numbers, and in steady state AC circuits, voltages, currents, and impedances, they are complex number. Real for DC, complex for AC. That's the only difference. Other than that, all the methods, theorems that we have studied in last few classes, like Thevenin theorem, Norton theorem, then what, superposition, nodal method, mesh method, everything is applicable for AC circuits as well when we use phasor values. Okay, so maybe we see some example problems to make this point more clear. Okay, so let us take some example problems. Okay, so here is one circuit, and we have L, C, R, everything connected together, and voltage and currents are given in their phasor forms. Okay, now we have to find the phasor value of this I bar, this current through the resistance. Can you suggest me how can we do this? Anyone? It's actually very simple.
First we'll convert to voltage equivalent,
Find the
sir.
Thevenin
And do?
equivalent first between
Yeah,
that point.
Thevenin equivalent.
Okay, we don't need to apply those
We can do simple addition.
Yes, yeah, I mean, first look at the questions for a while, okay? So often questions may be solved very easily. Like here, if you consider this lower node, okay, call this node A, if you just apply Kirchhoff's current law here, we are done. Okay, because the current coming from the left side is how much? It is minus 5 angle 0 degree, and the current coming from the right side is 10 angle 60 degree. So I bar will be equal to the sum of these two currents, minus 5 angle 0 degree plus 10 angle 60 degree. Okay, you can do this algebraically, or you can draw a diagram, whichever you like. Let me draw a diagram, this being the first question. So suppose this is the complex plane. So minus 5 angle 0 degree, that will be here, left side.
Or is it 5 √3 angle 90?
Absolutely right, absolutely right. Okay, so this is minus 5 angle 0 degree, and 10 angle 60 degree will be double in length at an angle of 60 degree. This is 10 angle 60 degree. Okay, so if you decompose this in real and imaginary part, then this real part will be plus 5, imaginary part will be sine 30 into 10, that is 5 √3 Okay, this is the imaginary part into J. So now when you add all these quantities, plus and minus 5 will cancel and we will get only J5 root 3. This is in ampere, which is also same as 5 root 3 angle 90 degree, as you have said. Okay, fine. Now maybe we take more questions. Okay, so look at this circuit. We have two parallel branches and there is a current source. We have to find the voltage, phasor voltage between A and B. How can we do this? Anyone? Okay, so let me ask, how much is the total impedance Z between A and B? Okay, so from from this part, how much is the total impedance? Okay, so we have two branches. Okay, the left side branch has an impedance of 5 and minus J3 in series, so I'm simply adding them. And then the right side branch has 5 plus J3 impedance. These two are to be combined in parallel. Okay, this is in ohm. So how much that will be? 5 minus J3 into 5 plus J3, product of the two divided by the sum of the two.
3.4, sir.
I guess you are right. Okay, so here
Yes,
the
sir, 3
numerator will be 34 by, yeah, right. So 34 by 10, absolutely. Okay, so if so, then how much is the voltage VAB? That will
It
be
is
simply
Impedance into that ampere,
yes, excellent.
5.
This current multiplied by ZAB,
17.
which will be 17 angle 30 degree
30.
ampere. Okay, if you want, you can also write in rectangular form. That will be 17 cosine 30 degree plus J 17 sine 30 degree. Sine
It would
30
be
degree.
volt, sir.
Yes.
It would be volt.
Oh, yeah. Thanks a lot. Volt, yeah. Okay, so any question here?
No, sir.
Okay, so let us see what is the next question. Okay, so
Sir,
yes,
here I have one doubt, sir. In that previous one,
Hmm?
in we got the impedance, but like, do we have to also get like that angle, whatever it's making, that for ZAB?
Right.
Then
In this particular case, this is with angle 0 degree. So
0
this is
degree.
with 0 degree. But in general, it may not be 0 degree. So then you also have to.
yeah, so like, how will we get it, sir? Like, if it is in parallel or so.
Okay, so
Uh,
let me see
then
whether I have any.
We will get a complex number, no?
We will get a
So it
complex
only
number.
the argument.
I think we
okay,
will have
like a
examples.
vector, we need to get that vector again then,
Yeah.
So
So
we'll get a
I
complex
guess.
number
I
so
think
we
we
can
will
find
see
capacity.
examples
Okay,
where,
complex number.
yeah, where this
And
is
a
not 0
complex number
degree.
angle we have to get.
Yeah.
Yeah, J will not get cancelled, so we'll get a
Right.
mixture of
Yeah.
real part and imaginary part.
Yeah. Okay. So
Okay, right.
let me take more questions. If your doubt
Okay, so
remains, you
like
can ask.
this one, actually we will write it like 3.4 plus J into 0 then,
Yes,
actually this
absolutely.
impedance.
Yes. You can also write it
Okay, fine, got it.
3.4 plus J0. Absolutely. Yeah.
Got it.
Okay. Acha. So now let's look at this question. We have to find the Norton current from P to Q. What is Norton current? Norton current is the short circuit current. If we short P and Q, how much will be the current? Okay, let this be ISC, short circuit, ISC. So question is, how much is ISC? That is the question. Okay, so how, any observation you would like to suggest?
Sir, we like in DC will we remove 25 ohm and only like make the current go through, no, let's only get to current source or something.
Yeah,
Or first
so
we will get the Thevenin equivalent here and then do.
yes. What you are suggesting is that you consider these two together and convert it into a equivalent voltage source. So that voltage source will be 16 to 25, that means 400 volt in series with 25 ohm, and then we can further simplify it. That is one way. Yes, I admit. Okay, acha. But here we have one observation which will make the problems little simpler, which is that you see this capacitor is in parallel with a short circuit path. Now, so the impedance of the short circuit is 0, and this capacitor has some non-zero finite impedance. Therefore, whatever current comes here, if that is I, that will completely go through the short circuit path and nothing will go through this capacitor. So therefore we can actually forget the presence of this capacitor. Okay, so we can say that this current will also be equal to ISC. Okay, because there is a short circuit path, zero impedance path, this current will completely go through that. So this way the circuit becomes.
So I didn't get, sir.
Yeah, so acha, suppose I call this gray colored current I. Okay, then at this point, call this point A. If we apply current divider rule, how much will be ISC? So I can then write ISC will be equal to I multiplied by the impedance of the other path, which is minus J50 divided by the sum of the two impedances of the two paths, which is minus J50 plus 0, right? So this becomes equal to I. So that means ISC will be I and no current will go through the capacitor. Okay, so that's why I'm saying this current is ISC and we can forget the presence of the capacitor because nothing will go through it, right? Okay, now yes.
In DC circuits, there is no current through capacitor. I agree, but in AC circuits, there can be displacement current.
Okay, no, don't make
Yes, sir, that's what I meant.
don't make life so complicated. So suppose I call this current IC, C for capacitor. Let me see how much is IC. Okay, I and suppose this is I. Okay, IC will be I multiplied by 0, the impedance of the short circuit path, divided by 0 plus J minus J 50. How much is this then? This is 0, right? So the phasor value of the current going through the capacitor will be 0. Okay, so if you have further doubts, we can discuss later. Achha. Now we have to find out the value of I or ISC. Both are same. Achha. To do that, let me consider this point. Okay, call this point B. Okay, so let me apply current divider rule at B. Then how much will be this current I? I will be this total current of 16 ampere multiplied by so here we have two possible paths. So 16 ampere multiplied by the impedance of the
25
other,
parallel,
25
15
yeah,
upon
plus
25
20J.
divided by
25 plus 15,
J30 plus 15.
15.
Okay, so this will be the current. So if you simplify, what do we get? 16 into 25, the denominator will be, so this is 40 plus 30J.
40 plus
So
30J.
that means basically 50 with an angle tan inverse 30 by 40, 3 by 4. Correct? This is in ampere.
Yes, sir.
Okay, so now you can simplify this, whatever you get. Okay, so simplify. You can simplify this now. So let me
Minus 8.
okay, let me put it as a homework. Just simplify this complex number. Okay. Achha. Any questions so far?
No, sir.
Okay, so then let me see if I have another question. Achha. So in this circuit, the source voltage is given and we have to find the output voltage VO, okay, on the right side. Okay. Any suggestion? The voltage and the voltages are given in functional form. How much is omega here?
1 by RC.
Yeah, from this equation you
1 by
can
RC.
see omega is equal to 1 by RC. Okay, so if so, how much will be the impedance of, let me make some space. How much will be the impedance of this capacitor XC? Call that XC. How much will be that?
Minus RJ.
Okay.
R
So yeah, XC.
RJ.
Yeah, you are right. So that will be J by, sorry, 1 by J omega C, and omega is 1 by RC, so put RC above. So that comes out to be minus R, JR. Okay, so this is minus JR. So then this will be also minus JR.
Yes, sir.
Okay, Achha,
Yes.
now let's consider these two together in parallel. Okay, so what will be the impedance of these two in parallel? That will be
R by root 2 into
R,
1 plus J.
yeah, R into minus JR.
R into
Divide-
minus JR upon R plus R
R
minus
minus
IR.
JR, absolutely right. Okay, so this is the impedance of this circled portion. Now with this portion, let me add this series resistance and this capacitance. Okay, so plus R minus JR. So this is the total impedance, right? Let me call this Z. Okay, then if this current is I, okay, and if I call the phasor value of this voltage as VI bar plus minus, then I bar will be VI by Z. Okay, and if so, and if VO bar plus minus, if this is the output voltage, then how much will be output voltage? That will be I
VI minus.
Yeah, I multiplied by this in parallel
X.
impedance, which is R minus JR by R, R into minus JR and R minus JR. Okay, so now if you put the value of I, so from here we will get VO equal to VI, then R minus JR, R minus JR, and the denominator will be Z, which is this long expression. Okay, so please simplify this and tell me what do we get. Okay, the R will cancel from numerator and denominator. Okay, R's will cancel. So how much this comes out to be? Take a minute and tell me what.
VI by 3.
VI by 3? Okay, you are right. Okay, so if you simplify this complex
Yes, sir.
number, you will get VI by 3. Okay, so now, so we see that the phasor value of VO is 1/3 of the phasor value of VI. Now, the functional value of VI is given, which is capital VP cos T by RC. Then what will be the functional value of the output voltage?
BP by 3.
Absolutely right. So it will be VI by 3. I mean, since the phasor value of the output voltage is 1/3 of phasor value of input voltage, again the functional value of output voltage will be 1/3 of the input voltage. So that will be VP by 3 cosine T by RC. That is the answer. Okay, is it fine? Okay, so here comes our next question. The circuit is given. We have a 14-volt source and then some impedances connected in a complicated manner, and we have to find this current I. How do you suggest to solve this question?
So star delta
Very good. In which part?
in the top part.
Top part.
So
On
but
our
yeah,
level.
explain by
Yeah.
I can see that.
No, sir,
See,
lower part will be easy.
Yeah, I will prefer the lower part because the lower part
Yes,
is
sir.
completely resistive. So
Yes, sir, easier.
yeah. So
That is.
let me copy it. Okay, and let me convert this lower part into the equivalent star. Okay, so we will have 3 impedances in general, but since all are resistance, it will also be, yes, you are right, and each of these will be, so each of these will be 6 into 6 by 6 plus 6 plus 6 ohm, that is 2 ohm. Okay, so all these 3 impedances are 2 ohm. Now, if so, if I call this node A and this node B, how much is the total impedance between A and B? How much is ZAB? Okay, this is
6.5
2 in ohm.
or 5, 7, 7.
I think you are right. So you see that we have 2 parallel paths. Okay, so
7.
yeah, so it will be 2 plus J4 in parallel with 2 minus J4, and then this lower 2 ohm is in series. Okay, this is in ohm. So we have 2 plus J4 into 2 minus J4 by 2 plus J4 plus 2 minus J4 plus 2. This is in ohm, and if you simplify, you will get 7 ohm. Okay, so then what will be the answer? I bar will be 14 angle 0 degree into 7.
14.
Sorry, divided by 7. So that is
20 degrees.
2
angle.
angle, yeah, absolutely right, 2 angle 0 degree. Okay, so
So can we have the balanced Wheatstone bridge in this condition?
we don't know whether this I mean, this looks like a Wheatstone bridge, but whether it is balanced or not, I mean, it's not balanced actually.
No, because like there is minus J4 over.
Yeah, right. So, I mean, if you take the ratio of the opposite arms, you will see the ratios are not equal. Okay, yeah. I mean, the ratios of adjacent arms. Yeah. Okay, so here is the next question. A very complicated circuit is given, but the question is very simple because we have to find this current I flowing here. Okay, we don't have to solve this circuit completely. We don't need to find all the currents everywhere in the circuit. We only need to find one particular current flowing through this inductor. Okay, so what is your suggestion?
Write KVL in one loop.
Yeah, you are absolutely right. Okay, if this current is I, then how much will be this current here? Okay, suppose this is I ampere. Okay, then how much will be this green current? That is I
I plus
minus
1 angle 0.
I minus 1, right?
Minus.
I minus 1, yeah.
Sorry, yeah, minus 1, yes, yeah.
Yeah. So this is I minus 1. Achha, now let us consider, let me name it A, B, C, D. Just consider this loop A, B, this.
Sir, is it minus 1J ampere?
I don't know. I don't remember the answer. I have to calculate. Let me calculate. Okay. So just let me redraw. So just consider.
So we can take the upward right side
Yeah, this
triangle.
upper
Sir, if
triangle.
we apply BCD in the
B,
KVL.
Yeah, this one,
C,
this
D,
one.
we cannot, because in the loop BCD we have a current source and we do not know the voltage across a current source.
Yeah. Sorry.
So let us
okay,
use
sir.
the
No, sir, then
yeah.
minus result.
Okay, so if we do this, then starting from A, okay, so apply KVL over A, B, C, D, A. So starting from A to B, there is a voltage drop of minus 1 multiplied by I into 1, I minus 1. This is a voltage drop. Then B to C, another voltage drop, which is I into J1. Okay, and then C to D, there is a voltage rise, so plus 1, angle 0 degree means 1 itself, and then from D to A, voltage drop of minus 1. Okay, so this is equal to 0. Now you see a lot of things cancels, this cancels, and from here what do we get? Let me see. We have minus I common, we have minus 1, just a second please, minus 1 minus j, and then plus 1, the right side will be minus 1. Yes.
Minus 1.
Yeah. Okay, so if I make this plus, plus and plus, okay, so then we get I equal to 1 by 1 plus j. Okay, you can further simplify it. This will be equal to 1 by 2 angle, how much will be the angle? Minus 45 degree.
And it's 40.
This is in ampere. Okay. Any questions so far?
Sir, so when we're dividing voltage here, sir, we can do it the same way like we are doing in normal DC one itself, sir. So
Yeah, I
like
mean
if VA is some
that's
X, then VD will be X plus 1 angle 0 degrees. Like that we can do.
right. Yeah. So if I, as you are saying, if V, this is VAB, say plus minus, then phasor, then VAB will be the current going from left to right, which is I minus 1, and the impedance, which is into 1. Likewise, yeah.
Okay. Okay. So like in this one, what if I take VAD? In that also, like
VAD.
VAD, I can take plus 1 angle 0 degrees.
So
Sorry, right, sir? I
VAD,
mean, same way that we do in DC.
yeah. So if I write VAD like this, say left side plus, right side minus, suppose, okay. So then VAD will be equal to, so I'm taking left side plus and right side minus, however the source is in the opposite direction, so I have to write it minus of the source value, minus 1 angle 0 degree, likewise.
Got it, sir.
Okay. Acha, so here is another question, another bit complicated circuit, but the question is simple because we have to find only one voltage, V2, that is the voltage at this point. So I will first ask you for your suggestions.
Sir, V2 with respect to which? Sir, V2 with respect to which?
One point is already grounded, man.
This point is the grounded, na? So this is the reference
Okay.
point. Yeah.
So we'll turn that left side part into Thevenin equivalent and then simplify and do it, sir. Right? Or
You can do
and then
it.
4 ohm will remove, I guess.
You can do it, but there is, I mean, at least I
Sir,
think
will
there is.
we remove the 4 ohm here because we can short the 10 volt is already connected.
Yes. One very good observation. This observation is that 4 ohm resistance has no significance. I mean, will not come into calculation. Will not come in calculation. Yeah, very good. So that is one thing you can do. Okay, very good. Yeah. Acha. So since we have to find only one voltage, okay, so let us try to write some circuit equation, only one equation in terms of V2, which we can solve and get the value of V2. Okay, so try to write some Kirchhoff's law in terms of V2, from that we can solve V2. Okay, so another observation is that V1, the value of V1 is how much? It is V2 plus 10. Okay, because of this 10 volt source. Okay, if this is V2 volt, if this is V1 volt, then V1 is V2 plus 10, 10 angle 0 degree. Okay, then now let me do it in this way. Consider this upper portion of the circuit. Okay, and let me calculate how much is the total current entering this portion. Okay, total current entering the blue portion is how much? So here we have 4 ampere.
4 into minus 3j upon 6 plus 3j.
No, let me do this in branch wise. Okay, so this branch, then this branch, and then this branch, and then we can add them all together. Okay, so the first branch has 4 ampere entering. Then in the second branch, actually V1 bar divided by minus J3, this amount of current is coming out, coming downwards. So let me put it minus. Okay, then in through this 6 ohm resistance, V2 divided by 6 is going out, so minus. And through this inductor, V2 by J6 is going out. So this is the total current entering this portion, and this should be equal to 0. Okay, because yeah, because you know what is the reason. Fine. So now if we now this equation has two unknowns, V1 and V2, but we already know that V1 is equal to V2 plus 10. Okay, so now we have one equation, one unknown. We can just solve for V2. So let me, if I say multiply everything with 6, okay, so then I will get 24. Here I will get 2, 3 will be gone, minus minus becomes plus, this 6 will be gone, this 6 will be gone. I can bring this j in the denominator to the upstairs, so make it plus j. Okay, is it correct so far? And then, oh, I missed this j here, and please check my calculation. And so we have 24, then minus 2jv2 plus, not plus, minus 20j minus v2 plus jv2 equal to 0. So you can, I think you can solve it. Okay, solve this as a homework. Fine?
Sir, I have a doubt.
Yes, please.
Sir, why you didn't consider 4 ohm in calculation?
4 ohm, I mean, see, the way I did it, 4 ohm never came into picture, na? So I considered this blue part, and I'm calculating how much current is entering this part. So anyway, this 4 ohm is completely inside the blue portion. So I'm considering only the branches or lines which are going across the boundary, so that current can go from outside to inside or inside to outside. Okay, so this anyway this inside portion is not coming in picture, no?
Okay, sir.
Sir, I wanted to ask, prior to finding it, for example, can we comment on how much current the ground supplies to circuit?
How much current? The ground so you are asking how much is the current here, right?
Yes, sir. Can we comment
Ground won't be
on it?
supply any current.
Ground, yes, excellent, absolutely. Ground won't be supplying any. I mean, this current will be 0 because there is no other path. So from, I mean, between ground and this circuit, there is only one path. So if some current is going, that must also come through some return path, no? But there is no return path, so this current must be equal to 0. Okay.
Okay, sir.
Yeah, so now you can actually verify this. Once you get the value of V2, then you put the value of V2 here and add those currents to get and see whether that is 0 or not. Anyway, there is no path, no other return path, so it should be 0.
Yes, sir.
Yeah. Okay, so shall I think we will solve more questions later. let me discuss some theory, and then we will solve more questions. Okay, so now we shall talk about the power in AC circuit. Okay, so consider we have an impedance. Suppose this is Z angle theta, some complex number, and let the current through it be I, and the voltage across it be V, and suppose that IT is equal to say Im sine omega t, okay, and then Vt will be some Vm sine omega t plus theta. Okay, you can easily see that Vm must be equal to Im times Z. Okay. However, the question is how much is the power input to this impedance. Okay, so power input, that means coming from outside to inside to this impedance, is given by Vt into I, so call it Pt, that is Vt into It, according to the directions of voltage and current that we have considered. This will be a power coming inward. Now if I write this as Vm sine, so let me write this way, Vm Im, we will have sine omega t and sine omega t plus theta. Okay, and I can also multiply this with a 2 and then divide it by 2. Okay, so then it becomes, or let me do it in this way. Let me divide this by root 2 and root 2. This is same. Now Vm by root 2 is nothing but the RMS value of voltage, and this is IRMS, and then this 2 sine, this is like 2 sine A sine B, so you can expand it as cosine of the difference of these two, which will be theta, minus cosine of the sum of these two angles, which will be 2 omega t plus theta. Okay, so we have these two terms, and this power is a function of time, we can see. So this power will change, power input will also change periodically, cyclically. But now let us calculate the average value of the power. Okay, so average power input, how do we calculate? That will be basically time average of Pt. So integrate that over time, say 0 to t, and then you divide that by time period, capital T. Okay, so that will be, let me just copy this, copy, paste. Okay, and we have to integrate it, so let me integrate it, 0 to t, Vrms, Irms, they are constant, so outside the integration, I missed a dt here, here also dt, and then we have to divide this by capital T. Okay, now inside the integration we have two terms. One is the second term is a function of time t. We have cosine 2 omega t. Okay, so if you average a cosine function over complete cycle, that will give you 0. So the second term will give you 0, and the first term cos theta is not a function of time. So when you take the average, it's not a function of time, so it will it is just a constant, so we will get VRMS IRMS into cos theta. Okay, so is this derivation okay with you?
Yes, sir.
So this is the expression.
Yes, sir.
Yeah. So this is the expression of average power consumed by this impedance Z. Okay. Acha. So this is the formula. Always RMS value of voltage, RMS value of current multiplied by cos theta, where theta is the phase angle difference between the voltage and current. Okay. Now, say average power, as we saw, this is VRMS IRMS cos theta. Here, this part, VRMS IRMS, this is called apparent power. Okay, but this is not the actual average power being consumed. If it were a resistive circuit, DC circuit maybe, then the power would have been just the product of voltage and current. But here in this AC circuit, we have one extra term, cos theta. This is called the power factor. The product of these two, apparent power and power factor, gives you the actual power, actual average power being consumed. Okay. Achha. Now observe for an inductor. Okay, if we have Z equal to say Z equal to J omega L, then how much is theta? Theta is 90 degree.
90 degrees.
Okay. Similarly, if we have Z equal to minus J by omega C for a capacitor, then theta is equal to minus 90 degree. For both these cases, we have cos theta equal to cos 90 degree plus or minus is equal to 0. Okay, so that means if we have an inductor or a capacitor in place of Z, then the average power consumed by it will be 0. Why is that so? Okay, so let me so consider an inductor. Suppose this is L, this current is I, voltage V. Okay, and if I draw the graphs, suppose this is voltage, how will the current graph look like? We discussed it yesterday. The current will be also sinusoidal, but at an phase difference, at a phase angle of 90 degree from it. Okay, so this is 9. So here omega t equal to 90 degree. This will be the current. Now, to get the power power is simply Vt into It. We have to multiply these two graphs. And if we do that, okay, so at these points here, 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 either the voltage is 0 or the current is 0. So therefore power will also be 0. And then then consider this region. In this region both both voltage and current, both of them are positive, so the power will be positive. It will be maximum in the middle part and then 0 on the both side. Okay, so this will be the graph of power here. Then in the next portion, here current is positive, voltage is negative, so again the power will be negative and it will look like this. Okay, so in this way, if I draw this graph of power as a function of time, you see half of the times it is positive, half of the times it is negative. Sometimes power is coming from outside to inside, sometimes it's going from inside to outside. Overall, average power coming inside is 0. So we see average Pt is equal to 0. The same thing applies also for an capacitor. Okay, you consider a capacitor, capacitance C, current I, and voltage Vt. Okay, if we draw the graphs, if this is the voltage, how will the current graph be? It will be leading the voltage by 90 degrees, so it will be like this. Okay, so current comes first and then the voltage. This is the current and here is the voltage. Again, if you multiply the two at these points, it will be 0. Okay, now here this is positive, here it is negative, positive, and so on. Okay, so again we see average power is 0. But what happens for a resistor? If this is I, if this is V, draw the two graphs and let's see what happens. If this is the voltage, how will be the current? It will be in the same phase, magnitude may be different. Okay, so this is IT, this is Vt, and if you multiply the two, what do you get? We get here 0, here 0, here 0, and in between positive, it will be like this. Okay, and again two negative numbers will give positive when multiplied, so it will be like this. Okay, so observe that here Pt is always greater than equal to 0 and average Pt is also definitely greater than 0. Okay, now any questions so far? So now,
No, sir.
yeah. So now let me come to this equation of power once again. Okay, let me make some space here. Okay, so for our general impedance, this was the expression of instantaneous power at any time, and for all time. Okay, now, so this is this we can write as Vrms IRMS cos theta minus, let me expand this cosine term as cos theta cos 2 omega t and plus sin theta sin 2 omega t. Okay, let me do a few more steps. So I can write this as Vrms IRMS. Then if I take this cos theta common, I have 1 minus cosine 2 omega t and plus Vrms IRMS sin theta sin 2 omega t. Okay, so we have two terms. Now you observe that the first term is always either greater than 0 or equal to 0. Okay, cos omega, so 1 minus cos 2 omega t is always greater than 0. It can go from 0 to 2. Okay, and the second term is oscillating between positive and negative. Oscillating between positive and negative values. And for this, the average value is 0. Average value of sin 2 omega t will be 0. Okay, but for the first term, how much is the average value? For the first term, the average value will be Vrms
IRMS into cos theta.
into cos theta. That is basically the overall average power. Okay, yeah, right. Now, the graph of the first term, the graph of this first term will be similar to the graph of this power in this resistive circuit. Okay, however, the graph of the second term is similar to the graph of the power of either the inductance or for the capacitance. Okay, so the first term is similar to a resistance, and this term is similar to A and R or and L or C. Okay, now this first term is called the active power. Okay, so this is called the active power. Actually, the coefficient of this first term, that means this number, okay, the coefficient is called the active power, and the coefficient here is called the reactive power. Okay, so here you observe that the term corresponding to the active power is always positive. That means always power is consumed. Okay, so but the term corresponding to the reactive power is sometimes positive, sometimes negative. So that means reactive power is sometimes going into or sometimes going out of the impedance Z. Okay, sometimes it's coming in, sometimes it's going out. So overall average is equal to 0. That is the property of the reactive component of this power, whereas active power is always greater, this part is always greater than equal to 0.
Hello,
Okay.
sir. Sir, why in this case cos theta is not less than or equal to 0?
When can cos theta be negative? Only if theta is greater than 90 degree or less than, I mean, so since you have asked, let me try to tell that briefly. Okay, so consider the impedance diagram. Okay, suppose you take a resistance R, with that you take some inductance in series j omega L, some capacitance minus j by omega C, and now if you add all this, the total impedance, that complex number will be always on the right side of this diagram. It cannot be on the left side. Okay, so the total Z will be on the right side. Okay, if you when they are in series, okay, in series. Now, if you consider them in parallel, then what can we do? We will first take the corresponding admittances and then we will add. Okay, so suppose this is 1 by R. Okay, then suppose here we will have 1 by j omega L, admittance corresponding to an inductor. Here we will have j omega C. Okay, so we are considering R, L, C in parallel. Okay, so this will be the total. Now when we add it, you will get the total admittance. So Y total admittance is again on the right side. Right side of the complex plane. Now if you calculate Z equal to 1 by Y, on which side that Z will be? Y is on the right side. So where will be Z? If this Y is equal to Y angle say theta, then Z will be
Minus
1 by Y angle minus theta. Okay, so if this is theta, minus theta will be on the downward side, but that will still be on the right side. Okay, so this will also be on the right side, will be on right side. So in this way, no matter whether in series or in parallel, no matter how you combine R, L and C, the angle of the total impedance, equivalent impedance, will always be on the right side. That means from between minus 90 and plus 90. And in that region, cos theta is always positive, right? So cos theta therefore cannot be negative. So does that answer your question? Who asked?
Yes, sir.
Okay, thank you. So, so what I was saying that this reactive power is the component of power that goes into and out of an impedance periodically. So overall consumption is 0. We will come back to the significance of this reactance power in a while, but before that, one more thing I want to tell you, which is about complex power. Okay, so once again consider an impedance Z angle theta. Now let me write the voltage and currents in the complex notation, in their phasor notation. So this is I, this is V. Okay, and suppose suppose this is I is equal to I RMS with an angle of what can I take, phi naught, some arbitrary angle, and then V bar phasor value will be of this form V RMS angle will be phi naught plus theta. I will define, so the term complex power as the product of V and I star. Star means complex conjugate. Okay, so star means complex conjugate. Okay, so this is the definition of complex power. Call it P. Again, this will be a vector, I mean complex number. Now,
what is its use, sir?
Yes.
What is its use?
Yeah, that's what I'm going to say now. Okay, now, so this P bar is how much? So here we have V is V RMS angle phi naught plus theta, and I, this is I RMS angle phi naught. We have to take the complex conjugate of this. When we take complex conjugate of a number, what do we get? This angle, yes,
Minus
this
angle.
angle will become minus, negative. Okay, and then it becomes VRMS, IRMS, and the angle will be theta. Phi naught and minus phi naught will cancel. Now, if I expand this in rectangular form, I will get VRMS, IRMS cos theta plus J VRMS, IRMS sin theta. What do we see here? We see that the real part of this complex number, complex power, is same as the active power which we have defined earlier. Okay, so you see the active power is VRMS IRMS cos theta, reactive power is VRMS IRMS sin theta. Okay, so and this imaginary part is the reactive power. So in this way you can get the active component and reactive component of the power just using this formula phi I star, which is called the complex power. Okay, that's so easy. And yeah, now one observation, if theta is positive, suppose if z angle theta, this impedance equal to r plus some jx. Okay, so then that means theta is equal to tan inverse x by r. Now theta will be positive, so theta is positive when x is positive. That means for inductive impedance or inductance, and theta is negative for capacitive circuits. Now you also observe when theta is positive, then sine theta will be positive, and if theta is negative, sine theta will be also negative. So that, what does that mean? The reactive power consumed by inductive impedance is always positive, and reactive power consumed by capacitive impedance is negative. Okay, but when I say it's consumed, it doesn't mean that it is literally consumed or consumed overall in an average sense. Okay, I mean, only in mathematical notation the sign of this number will be positive or negative. That's what I mean. Okay. Acha. Now, so the observation here is that the reactive power consumed by an inductor and that by an capacitor, they are opposite in sign. Okay, this you keep in mind. Now let's come to the significance or importance of power factor and power factor, reactive power, etc. What is the importance of these terms? Consider that we have a power system which has a generator generating some voltage, and then we have long transmission lines which brings power to our homes, and then in the other end we have our homes, our gadgets connected here. Okay, suppose this, we call this the load. This is the load side. Suppose this impedance is Z angle theta. Now let this up the voltage from here to here be equal to V. Okay, and the current is coming here. Let me just write the RMS values. This is VRMS, this is IRMS. Then the power consumed by load will be equal to VRMS IRMS into cosine theta. Now VRMS, that is the voltage supply, should be remain fixed. Okay, so VRMS is a fixed voltage, is fixed. For example, this is 240 volt, 50 hertz in our houses, something like that. Then suppose we need, and let me call this power as W. Okay, then we can write here that IRMS is equal to W by VRMS cos theta. Now, for a fixed amount of power requirement for a given amount of required power, that is W, the value of IRMS is inversely proportional to cos theta. Okay, so lower the value of power factor, higher will be the current. Okay, so lower, so this is 1 over power factor. So lower the power factor, higher is the current. However, power consumed is constant, although power consumed is constant, is the same. Okay. Any question? Fine. So now what happens? I can, if I have a lower value of power factor, the power consumed may remain same, but the current coming through the transmission line will become higher, and the transmission line also has some resistance. Okay, now the transmission line also has some resistance. So if IRMS is higher, power loss in transmission line will be more. Therefore, efficiency of this power supply system will be low. More power is lost than that compared to how much is actually used. Therefore, it is always good to have higher power factor. Okay, so you may say that why does the power factor matters? If I am consuming a certain amount of power, I should pay my electricity bill based on only the consumed amount of power and not on the amount of current that I am drawing. But that is not really the truth, because if I also draw more current for a small amount of power required, I am actually causing more amount of power loss for the power supply agency. So that is a loss for them. Okay, so power factor should be high. Now, another thing to notice is that complex power which is equal to V RMS I RMS cos theta plus J into V RMS I RMS into sin theta. Okay, the first part being the active power, and the second part is the reactive power. Now, when cos theta is low, then sin theta is high. Okay, if cos theta is low, root over 1 minus cos square theta, that is sin theta, that will be high. So that means reactive power will be high. However, reactive power is not the power which we consume on an average sense. Reactive power is the power that comes and goes, comes and goes, comes and goes. Okay, but that is not consumed on an average sense. Now this situation is something similar to, analogous to this situation. Suppose, there is some, say, online shopping agency, online shopping market, telemarket, and here I am the consumer. Okay, I can order some dress, and the dress will come, and I may just use it and keep it, or I may also return it if I do not like, and I may then reorder a new dress. In this way, I can reorder the dress maybe 10 times and then finally keep the last one. And then I can say, okay, I have kept only one dress, so I should pay for only one dress. Why I should pay more than one dress? But you have to also keep in mind that there is some transportation cost also involved for this dress to come to me and return back 10 times. Okay, so which is a loss for the the shopping market. So therefore, the situation when we are consuming reactive power is also analogous to this this situation. If we take reactive power and if we return it back, although I am not consuming it, but when I am taking it through the transmission line and returning it through the transmission line, part of it being lost. So therefore, it is always better to have higher power factor. That means lower reactive power. So we should always try to have higher power factor and lower reactive power. Okay, that's the essential lesson which we learn from here. Okay, so do you have any question so far? Anyone? Is it okay?
I just didn't get the last part, sir. The last one.
Yeah, so I said we should have higher power factor, that means cos theta. Okay, so that the sin theta is low. If sin theta is low, then the power which is oscillating between the source and the load, that is low. And if that is low, transmission loss, the power loss in the transmission line will also be low. Another way of viewing that is that if cos theta is high, then IRMS will be low here. And if IRMS is low, then the power loss in the transmission line will also be low, because how much is transmission loss? Okay, so transmission loss is equal to IRMS squared multiplied by R, where R is the resistance of the line, which is not zero, which cannot be zero. And when we are considering several kilometers, thousands of kilometers of hundreds or more kilometers of transmission line, the resistance is not zero, of course. Okay, is it fine?
Got it, sir.
Yeah. So now I will end with one more small thing, which is like this. Okay, so suppose we have, let me copy this previous diagram. Okay, so suppose here this Z is equal to R plus j omega L, some resistance and some inductance. Okay, so then and if the phasor voltage is V, where do I write? Let me overwrite. Okay, so this suppose this is V RMS. Achha, let me write in this way: V bar plus minus, and where V bar is equal to V RMS. Let me take the angle to be equal to 0 degree for simplicity. Okay, then how much is IRMS? How much is I? This current, phasor current, that will be V bar by Z bar, which is V bar by R plus j omega L. Okay, so that will come out to be V RMS, and this will become, if I multiply R minus j omega L in the numerator and in the denominator, we will get this R square plus omega square L square. Okay, so this is the current. Now complex power is how much? That will be V RMS angle 0 degree, so we can and then multiplied by I bar star, so that will be V RMS, then V RMS by R square plus omega square L square R. Here we will get plus, instead this minus j will become plus j when you take the conjugate j omega L. Okay, so if you expand, you will get some, so let me write VRMS squared into R. Please check my calculations. I am doing it very hurriedly here, and plus VRMS squared into J into omega L by R square plus omega square L square. Okay, so this is the reactive power, and this part is positive. Okay, positive reactive power. Okay, and here power factor is equal to cosine of theta. How much is theta in this case? So this is Z angle theta. So theta should be tan inverse omega L by R. So we will have tan inverse cosine tan inverse omega L by R. Now larger this inductance is, lower will be the power factor. Okay, larger this ratio omega L by R, or I mean you know what I mean, larger the inductance, more will be the less will be the power factor. Okay, acha. Now I can do one thing. I can connect a capacitor in parallel with this load, call that C. Okay, so if I connect the capacitor in parallel, okay, so how much will be the XC impedance of the capacitor? That is minus J by omega C. Okay, then if I call let me write this I bar here, let me write it this way, let me put it here. I bar was here, this was I bar, the current which we calculated earlier. Now this capacitor will also take some current, call that IC bar. Okay, so how much will be IC bar? That will be V bar divided by this impedance minus J omega C above. Am I correct? V bar by minus J and omega C above. So now how much will be the complex power taken by the capacitor? That will be V RMS into 0 degree, then this current which is V bar omega C by minus J whole star, so that is V RMS, then V bar is V RMS, it omega C by minus J star, so that becomes V RMS squared omega C, and this minus J will become plus J when we take the conjugate, and then this will become minus J V RMS squared omega C when you bring this J upstairs. So now this is negative, so we have negative reactive power. Now our load is also connected, this capacitor is also connected. They are both consuming some power. So if I consider, this is the last line I am writing, the total power, total complex power taken by the load and the capacitor together is how much? We will just copy this, copy, paste, and we will add this. Okay, so now if I choose the value of this C properly, then this total reactive power can be made 0. Okay, so we can choose C so that the total reactive power will be 0, will become 0, and then also at the same, so the total power factor will become 1. Total power factor will be equal to 1. So I mean cos theta will become 1. So what is the advantage of doing that? In doing this, the value of this total I mean I plus IC will become much lower than I itself. So this current can be lowered and therefore transmission loss can be lowered. This is called power factor improvement. That's all. Okay, so this is called power factor improvement. Okay, so I shall stop here.